Angular momentum slash collisions. We've talked a little about this in class, but let's just look at a couple of simple cases. Imagine that I have a rod that is pinned and has a length of 2 meters and has a mass of 2 kilograms. And imagine that I have a wad of clay coming in with a velocity of 7 meters per second, and a mass of half a kilogram. So what I want to do is think about this collision from the perspective of angular momentum. And to do that, what I'm going to do is calculate the angular momentum of the clay coming in. So I'm going to write capital L, which is close enough to angular momentum, and it's equal to R cross mv. And in this case, my R is going to be just L over 2, half the length of the rod, because it's pinned at the middle and it's going to pivot about the center point, multiplied by the mass, which is half a kilogram, and then multiplied by the velocity, which is 7 meters per second. And then once it collides, it's pretty obvious that the rod itself is going to spin. But we know that angular momentum is conserved, so this would be maybe my initial angular momentum, and then I'm going to set that equal to the final angular momentum, which is I times omega. So I need to calculate the I for this system. Well, the I for this system is going to be the I of the clay plus I of the rod. Well, the I of the clay is just the mass of the clay, 1/2 kilogram, multiplied by the length squared, multiplied by the radius squared, which is just 1 meter, quantity squared, plus the I of the rod, which is 1/12 times its mass, 2 kilograms, times its length, 2 meters, quantity squared. And remember, the I of the rod is something that we would either be given, or I guess you could derive. But the I of the rod is 1/12 mL squared. Okay. If I do this out, I come up with an L of 7/6 kilogram meters squared. Okay, so I'm going to come down here, and if I look here, plugging in an L of 2, I end up with a length of 2. I end up with L0 as a vector equals 3/5 kilogram meters squared per second. And that's going to equal I that I have here, 7/6 kilogram meters squared times omega. And if I do that out, and just to help make this clearer, I'm actually going to write this as 7/2 kilogram meters squared per second is 7/6 kilogram meters squared times omega. And if I do that, it's pretty obvious that this is going to end up looking like 6/2 radians per second is equal to omega. So that's cool. So I've calculated the angular velocity of the rod. The rod has an angular velocity of 3.5 radians per second. What I'm going to talk about next is what happens if the rod is free to slide. So the simplest analogy of this, and I'm going to go do this on the next one, is that I have a hockey stick that I'm going to model as just being having no blade, and a puck comes along and hits it. And so that what's going to happen is the center of mass is going to move off, and the stick itself is going to start rotating.